Okay, this is test number 4, problem number 1. It says find all the solutions to cosine of 2x plus 3 cosine x plus 2 equals 0. So first we need to rewrite cosine of 2x as 2 cosine squared of x plus, 2 cosine squared of x minus 1 plus our 3 cosine x plus 2, that equals 0. And now we can factor this. After simplifying, we have 2 cosine squared x plus 3 cosine x plus 1 equals 0. And let's factor, we get 2 cosine x plus 1 times cosine x plus 1 equals 0. Now we have multiplication equals 0, so we can set each one of these terms equal to 0. So we have 2 cosine x plus 1 equals 0, and cosine x plus 1 equals 0. So solving for x, we have cosine x equals negative 1/2, or cosine x equals negative 1. So x cosine is negative 1/2 when x equals 2 pi over 3 or 4 pi over 3. And since cosine has a period of 2 pi, we add 2 pi k to both of these to find all solutions. And cosine of x is negative 1/2 when x equals pi plus 2 pi k. So these are all of our solutions for this equation. Okay, this is problem number 2. It says find the equation, focus, and directrix for a parabola that has a vertex, the origin, opens right, and passes through the point P 7, negative 3. So, since we know that the vertex is at the origin and the parabola opens to the right, we're going to use the equation x equals 1 over 4p times y squared. We're given a point, so let's plug in our point that we know. 7 equals 1 divided by 4p times negative 3 squared, which is 9. And we need to solve for p. So we're going to divide by 9 on both sides. So we get 7/9 equals 1 divided by 4p. And let's cross multiply, so we get 28p equals 9. And so p equals 9 divided by 28. So now that we know p, we know our focus is at 9 over 28, 0. And our directrix is x equals negative 9 over 28. So I'll draw that directrix on the graph. Since x equals negative p, we know that that's our directrix. And now that we know p, we can find our equation for this parabola. And that is x equals 1 divided by 4p y squared. So x equals 1 over 4 times 9/28 y squared, or x equals 7/9 y squared. So this is our equation. We have our focus and directrix, and we know the graph will open to the right at the origin, and the focus is p distance away from the origin, so focus is p, 0. And there's our graph. Okay, this is problem number 3. We need to express cosine to the 4th t in terms of values of the cosine function with powers of 1. So we need to get rid of that fourth power of cosine t. So the first thing we want to do is we want to rewrite this cosine to the 4th t as cosine squared t times cosine squared t. And now we know a formula to rewrite these as 1 plus cosine 2t divided by 2. We have another one, so, and I'm sorry, this is times 1 plus cosine 2t divided by 2. So let's FOIL this out. So we get 1 plus 2 cosine 2t plus cosine squared 2t, all divided by 4. And if we pull out the 1/4, we get 1/4 times 1 plus 2 cosine 2t plus our 1. We're going to rewrite that cosine squared 2t as 1 plus cosine 4t divided by 2. And we can factor out now, or FOIL that 1/4 in. So we have 1/4 plus 1/2 cosine of 2t plus 1/8 plus 1/8 cosine 4t, and we need to combine this 1/4 and this 1/8, and that will be 3/8 plus 1/2 cosine of 2t plus 1/8 cosine of 4t, and these are all cosine functions with powers of 1, so we are finished. Okay, this is problem number 4. We need to verify 2 of the following 3 identities. We will go through all three of them. And so for A, we have 1/4 sine of 4t equals sine t cosine cube t minus cosine t sine cube t. We're going to work with the left-hand side here. We know we can use our double angle identity to rewrite this. So this can be written as 1/4 times sine of, we're going to use the double angle, so 1/4 times 2 sine of 2t cosine of 2t, and that equals 1/2 sine of 2t times cosine of 2t. And let's go ahead and use it one more time for that sine of 2t. So we have 1/2 times 2 sine of t cosine t times that cosine of 2t still. And we'll go ahead and factor in that 1/2. So we have sine of t times cosine of t times cosine of 2t. And we can rewrite that cosine of 2t, so we have sine of t cosine of t times cosine squared of t minus sine squared of t. And let's distribute that sine cosine t in front to both of those terms. So we have sine of t times cosine cubed t minus sine cubed t cosine t, which is what we needed to verify. So we are done. Okay, this is problem number B. It's we need to verify that 4 cosine x cosine 2x times sine 3x equals sine 2x plus sine 4x plus sine 6x. So we're going to work with the left-hand side, and we're going to rearrange our writing that we have. So we're just going to write this as 4 times cosine of x times sine of 3x, and then times our cosine of 2x. And we're going to use our product to sum formula. So we have the 4 still, and it's 1/2 times sine of x plus 3x, which is 4x, minus sine of x minus 3x, which is negative 2x. And then we still have that cosine of 2x outside. Let's get rid of that 4 and 1/2, so that becomes 2 sine of 4x plus sine of 2x, because we can bring that negative out in front, and that minus times a negative becomes positive, and all of this times our cosine of 2x. Now let's distribute that cosine of 2x in to both terms. So we have 2 sine of 4x times cosine of 2x plus 2 sine of 2x times cosine of 2x. And we're going to use the product of sum formula again to rewrite this sine 4x cosine 2x. So we have 2 times 1/2 sine of 4x plus 2x, which is 6x, and then plus sine of 4x minus 2x, which is 2x, plus our 2 sine of 2x cosine of 2x. Let's go ahead and get rid of that 2 and then 1/2. That becomes 1. So we have sine of 6x plus sine of 2x plus our 2 sine 2x cosine 2x is our double angle for sine of 4x. So that becomes sine of 4x. And we just need to simplify that, rather rearrange that to be sine of 2x plus sine of 4x plus sine of 6x, which is what we needed to verify. So we're done with this problem.
For this following problem, we are asked to verify these following identities, and we have cotangent of 2u equals cotangent squared of u minus 1, all divided by 2 cotangent of u. So let's take a look at the right side, because it looks like we have most stuff to work with, and start the problem like we always do. We always want to convert to sine and cosine, so I'm just going to do that right away. So cotangent squared is going to give us cosine squared of u over sine squared of u. Oops, it's really sloppy, pardon me. Minus 1 on top, divided by 2 cosine u sine u. Cosine u divided by sine u, excuse me. Alright, so we've rewritten that. You can't really read it too well, I apologize for that. But let's kind of clean it up a little bit, these fractions. So we see we could probably multiply through by sine squared of u, and we'll get rid of the fractions within the fractions. So I'm going to go ahead, we're going to do that, multiply the top and bottom by sine squared of u. So that is going to leave us with something that looks like cosine squared of u, because the sine squares drop out on top, minus sine squared of u. 1 times sine squared is sine squared. So on to the bottom, we're going to be left with 2 times a sine. We have 1 left because it wasn't a sine squared on the bottom. Sine of u times cosine of u. Now if we look at the top, we have the cosine squared of u minus sine squared of u. That is, if we remember, we have a double angle identity, and that just tells us that cosine squared of u minus sine squared of u is just simply equal to cosine of 2u. So on top, we're going to have cosine of 2u. And on bottom, we also see we have Dr. Allen's favorite identity, the 2 sine u cosine u, and that is just sine of 2u. So now we are left with a cosine 2u over a sine 2u, which is also equal to cotangent of 2u. For this following problem, we are shown a picture of a fighter plane, and we need to find the approximate angle of phi. So I've redrawn the triangle, or the plane as a triangle. It may be sloppy, but you get the gist of it, and we need to solve for the green angle phi. So this is looking like we need to maybe take advantage of b, because that's a lot in a straight line, and it touches phi, if you will. So we're going to have complementary angles. That total beta plus phi needs to equal 180 degrees. So using our triangle, looks like we can figure out beta, and then we can go on and subtract beta from 180 to give us phi. So in order for us to solve for beta, it's looking like we could use our law of sines here. So how about, we know the sine of 27, 27, divided by its opposite side, so 16.7, is equal to the sine of beta and beta's opposite side of 35.9. So now that we have that, we need to solve for sine of beta. So in doing so, solving for sine of beta, we end up with 35.9 sine of 27, all divided by 16.7. So if we punch that into our calculator, we are going to get 0.9759, which implies that beta is going to equal 77.4 degrees. So, solve for phi. We know that 180 degrees is equal to beta plus phi. Just because phi and beta run along a straight line in the complementary. So we know beta, so let's plug that in, and we'll end up with 180 minus 77.4 is equal to phi. Solving for that, phi is going to equal 102.6 degrees. For this following problem, we are asked to find the wingspan from C to C prime of our jet plane. So I've gone and redrawn C to C prime, a little sloppy, but I put in the values that we do know. We don't know the distance from C down to where the angles beta and phi were from our other problem that we just previously did, but we know that there's 4.8 feet in the middle that we know that distance, and then another distance d that is still unknown. We also have an angle beta. It's from our last problem, the same, 77.4 degrees. So we can kind of form a triangle, and we know the distance 16.7 feet from our diagram. So we inserted that for the hypotenuse. So we need to solve for the two d values, and eventually we'll just add them all together. So to solve for d value, we have an angle that we know, and we have a side length that we know. So let's just use a basic property of sine. So let's take the sine of the angle we know, sine of beta, which is 77.4 degrees. And that's going to be equal to our opposite, which is d, over our hypotenuse, which is 16.7. And solving for d, get sine of 77.4 times 16.7, and that is equal to, type it into our calculator, 16.3 feet. So we have d equals 16.3. So now, looks like to find the total wingspan, we have two d's, and we know 4.8. So that's going to give us our C to C prime wingspan. So let's just plug that in. 2 times 16.3 plus 4.8 will give us a value of 37.4 feet for the wingspan. The final question of number 5 asks us to approximate the area of the wing of the triangle A, B, and C. I've taken that triangle and redrawn it a little bit and put in information that we know. We know that we have a side length of 16.7 feet and another one of 35.9 feet, but we don't know the B to A length. So we might need to find that. We also know these angle measures. the 77.4 we found in the first part of this question. The 27 degrees, that's just a complementary angle of 153, as we see on the diagram from the plane that equals 180. So the remaining, we have alpha up there. I made it yellow. We need to find out what that is. Alpha is equal to 75.6 degrees. Okay, so we're asked to find the area of this triangle. The formula for area of a triangle, in case those who might not remember, your area equals 1/2 your base times your height. So, looks like we have a base and we have a height from the previous two that we could figure out, possibly. I also forgot to write in from the previous problem, we know h. H is equal to our previous d from our distance from part B. So that came out to be 16.3 feet. So we have the height, the 16.3. We need to find the base. So to do that, we can use our law of sines again. So we're going to have the sine of alpha. Excuse me. Let's use this. Let's solve this using the law of sine. So we have b is our unknown, but the opposite angle of that we found alpha to be 75.6. So the sine of 75.6 degrees is equal to, we can use another angle. Let's choose the 27-degree angle. So its corresponding side is 16.7 feet. All right. Sine of 27. Right in there. So we need to solve for b. Solving for b, we'll have something. b is equal to 16.7 times the sine of 75.6 divided by sine of 27, which equals, when we put it into our calculator, 35.6 feet. So then, using our area formula, we have all our variables to solve for this. So area equals 1/2 our base we found to be 35.6, and our height to be 16.3. It's supposed to be 0.3. But type that into your calculator, we get our area to equal 290.1 feet. Square feet, excuse me. For this next problem, we're asked to find the variables of this triangle. So we're going to have to use perhaps law of sine, law of cosine. Let's get started. Looks like we have two sides and one angle. Let's try to get A. Let's try to find the other side. So we do have our law of cosines that tells us when we have one angle and then two side measures, we can solve for A. So that equation would be A squared equal to B squared plus C squared minus 2BC cosine of our angle. We'll call that angle alpha. Call this one alpha. Alright, so when we plug these numbers in, we'll get A squared is equal to the opposite of beta, we'll call B. So it'll be B. It'll be 70 squared plus our other known sign. We can call that opposite of gamma. Call this C. C squared will be 4.3 squared minus 270 times 4.3, all multiplied. I'm kind of running out of room, excuse me. So multiplied by cosine of our angle alpha, with 23.67. So when we plug that into our calculator, a squared equals 4,367.1. But now we have to solve for a, so we have to take the square root of it. So a equals 66.1. So we solve for one side of the triangle. 66.1. Now that we have all the sides, we can start solving for the angles using our law of sines. So how about we solve for angle beta? We'll use our law of sines. So sine of beta, and the opposite of that is 70. Let's take our side we just found, the alpha. So sine of 23.67 divided by its opposite, so 66.1. So solving for sine of b, we are going to get 70 times the sine of 23.67 divided by 66.1. That is going to equal 25.2 degrees for beta once we solve for it. I'm going to erase this thing. Solving for beta, like I said, we get 25.2 degrees. So we have one angle. So now, angles of a triangle, they all add up to equal 180 degrees. So we have our angle that's 23.67. We have an angle that's 25.2 degrees. So, and then we have our angle gamma. That looks really bad. But we need all those to add up to equal 180. So let's add 23. Let's add our alpha and our beta up together. And then you subtract that from 180. I'm just going to skip this because it's basic addition, subtraction. For gamma, we solve for that equaling 131.1 degrees. So in order to find out that remaining angle, add up the two angle measures we know and subtract that from 180, and that's how we got our gamma. And I cannot draw a gamma. I apologize for that.